diagram is schematic of a positive controlled and a negative controlled. We all know what that is, right? My God Almighty, I spent weeks talking about it.
You grouped over real quick and you said an
I've talked about it dozens of times.
Automotive circuits, sometimes it's better to do this.
Drew a picture of one of them on the board.
What about the voltage regulator I showed you? It's positive controlled type A, or actually type B.
Regulator?
Negative controlled type B. Covered it extensively.
Positive control type A?
Actually,
go
that's
look
type
this up.
B.
What's that?
Positive control is type B.
Positive
Negative
control.
control is just where's the switch relative to positive
By
and
the
negative?
load.
Well, relative to positive and negative, really. It's both load and power source,
Okay.
right?
Load and power source.
Load and power source. We're going to use some of those words in our write-up.
Well, the bizarre thing is you can look on the internet all day long and nobody talks about it, but that's the reality of what we do.
Right.
We control on the negative side often with computers. We control
That's
on
what
the
you
positive
said. See,
side.
that's what you said. That's what you said in class. That's all you said.
Oh, I said it
A lot of times we
I even
control
drew pictures of
computers
pictures
on the
of
negative side.
transistors.
And that was basically
I drew pictures of transistors. It's not my fault nothing sticks in your head. I'm gonna get a flashlight sticking on the side of your ear. You see daylight coming.
Oh, you had to go that way.
yeah, okay, computers are
That's some tough love right there.
Oh, man.
Yeah.
All right.
I remember you said that.
I know I said it.
I know house would be like
All right, Andrews. Oh, Andrews.
shut off.
Negative. That would be positive.
Goes to RC, booze, camera,
Yes.
So, thanks.
Yes.
Negative, circuit's still active even when you flip the switch.
Kinder.
Right. I think
Still
so.
connected to the bat. It's still connected to the battery. The battery.
On the down one side. It's like
So you're not disconnecting the circuit from the battery. You're not meant with your
Yes.
circuit negative.
negative control.
So you're talking about the voltage regulator.
The voltage regulator is that way.
All right, let's finish talking about motors. AC type motors.
It's confusing.
It's confusing.
You gotta try to teach yourself.
Speaking of confusing, AC motors are confusing.
I want to know something to teach yourself.
Do you know what day our final's gonna be?
Yes.
Yeah, last day of the semester.
21st.
22nd?
21st
In this class.
in this class.
Are we having a test before the final?
We're gonna have a test next week.
Test next week.
So we're gonna have a test on the 14th and a test on the 21st.
14th and 21st.
That is correct.
Back to back.
It's a test on the 21st.
A test, but I'll go over it before we're done tonight.
I don't believe that.
Oh, I'm not.
So it's just the Wi-Fi service sucks tonight.
It sucks really bad.
Oh, dude.
It takes me forever to get on Google. I think if you guys do you guys reset the Wi-Fi every night?
I don't do anything with it.
Yeah, those things go.
If you get too many cookies and catches
Yeah.
on, you can just simply fix the problem by resetting it.
They go
Me,
stale.
I
You
don't-
gotta reset them, man.
Yeah,
So
I
you gotta
do.
Me,
back
I don't do
Wait
nothing,
10
don't
seconds.
touch nothing, don't know nothing. Try to avoid it all.
That's how I survived.
Don't touch the printer, don't touch. The only thing I touch is the laser printer, the laser
You
cutter.
got a haircut, no?
Was that part of the Delta?
I
Was
cut
that
them all,
the-
man. Gotcha.
Nice.
Number 2 blade, quarter inch.
Nice.
Wing, 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 wing.
Nice.
Oh yeah.
Cuts down on the shampoo bill.
Are you guys getting all that equipment from the Delta package? Or
No.
is that from the,
No, it's the final one. They remodeled the building 8, 9, 12 years ago, whenever it was.
they
They're
finally,
just now because they're just finishing
the
a
last
little motorcycle parking shed out there.
motorcycle part? Is that where they're going?
Well, that's what I'm calling it, just to annoy Lonnie. You guys, I'll have you guys park all your motorcycles in there too. We'll really get them pissed off. No, in the new shed out there.
Yeah,
Yeah.
hell yeah.
Don't do it.
When you
We
say
probably get 30 or 40 of them in there.
Do I get a party pass for that?
Yeah, no, because the building's closed. All right, AC motors. So in a DC motor, we talked about the notion that we have to feed it some DC, and we're going to have this switching device called the commutator. And so every time the little field, the current is driven through some set of the armature windings, those armature windings create some magnetic fields which act against the lines of force on the top and the bottom of those magnetic lines of flux going around the wire. So on one side they pull, on the other side they push. And that forces this spindle round and round and round. We talked about the idea that if we reverse the magnetic pole of the field, or we reverse the current being driven through the armature, we'll reverse the direction of the motor. But if we reverse both of those, the motor will go the same direction. Okay? In the world of AC, we're going to do something entirely different. The same basic idea will exist. We're going to have to take a magnetic field, and we're going to create a set of rotating magnetic fields that the original magnetic field will react against. So we're going to take the armature, which is the part that spins around, and in motors, in all cases, the part that spins around is the armature, because the armature is the output, right? And in this case, the output is spinning motion, or linear motion, or some physical motion. So the motor, the armature, always has to be the part that's moving. So in the world of AC, how do we make AC? Typically. Don't we take an electromagnet and spin it around inside a set of windings?
Yep.
And the resultant AC that comes off of there is a sine wave, which mathematically perfectly models rotary motion. Okay, obviously it's gonna model the rotary motion of the original thing causing it to be created in the first place. So we could take that electric behavior and wrap it in a similar winding. And as far as the rest of the world is concerned, inside that winding, the magnetic fields are going to be spinning around and around, just like they were when they were creating the electric flow. So in this particular case, as long as I've got 3 phases of winding, or in this case they're showing single, but I can show a magnetic field, magnetic field, magnetic field, magnetic field, and it just keeps going round and round and round. So as that's spinning around, anything I put in there that's magnetic will try to follow it. Okay? Now, we'll talk about what the difference between these two are, but the most common form of AC motor is called an induction motor. And in an induction motor, we're just going to induce electromagnetism in the part that's spinning. In the synchronous motor, we're going to use a permanent magnet in the armature. The part that's spinning is a permanent magnet. So its magnetic fields will try to very closely match what the AC is doing. Now, if I suddenly load it, it won't. But if I let it go without too much load, it'll actually stay very synchronous with it. Okay, now the other thing is, remember we said there was single phase and really 3-phase AC with 3 windings, so we can produce all 3 phases, or we could go between any 2 of the windings and have single phase, say 220, or we could go from the neutral across just one of the windings and have single phase 110 or 440, 220, whatever we ramped it up to. Well, an AC motor will work off of both of those. The downside is if we're just using the single phase, whether it's 220 or 110, the motor doesn't know which way to go. And in fact, it probably, unless it happens to stop in just the right spot, it probably won't be able to start all that well. Okay, but so we're going to have to do some things to get it to start. And to get it to start the direction we want it to. be kind of a pain in the butt. You go out, turn the bandsaw on, it goes the wrong direction. Turn it off, let it come to a stop, turn it on again. Yeah, oh, there it goes the right direction. Now you can use it, right? And that's not good. Now, with three-phase AC motors, they will go the exact same direction the generator goes, unless you happen to have the three phases not hooked up correctly. So if I hook up A to A and B to B and C to C, then it'll go exactly the same direction the generator's going. Now, if you stop and think about it, the only way to get it incorrect is to get two leads reversed, right? So if I get two leads reversed, what's going to happen? That's just going to go the other direction. So we don't care whether it's hooked up A, B, or C, or L1, L2, L3. We just don't care. Because what we're going to do is we're going to hook it up, and if it goes the wrong direction, we're going to shut it off, flip to any two leads, and then it'll go the right direction. Okay. Now,
And they're off.
I have a story to tell
Oh, good.
about that. You would think that when they build buildings,
They would stay in phase.
they would hook up the wires and see which way the motor spins. But according to design specification building processes, each contractor starts from here to wherever the last guy stopped and ends here. So the electricians don't have the authority to actually turn things on, they just hook it up. So they don't actually know, there's no way for them to know whether or not the motor's hooked up right, because they don't actually turn it on. So there's 7 three-phase motors in this building. Now you'd think 50-50 shot that each one would be either hooked up the right direction or the wrong direction, right? All 7 of them spun the wrong direction
In this building?
in this building. When they did the remodel, and everything hooked back up, they all went the wrong direction. It's just like, of course, I'm chewing on the electrician. Why didn't you turn it on? We're not allowed to turn it on. Design spec says we hook it up, we don't turn it on. It's like, well, you're an electrician, you know there is no way to tell which way it's hooked up because you don't get actually to see L1, L2, or L3. You decide what it is at the power head, but you don't know what it is from the, you don't know which way the generator is spinning at the nuclear power plant. Okay? Well, they got it backwards, but they got all of them consistently backwards, so there's that. I got to give them credit for that.
So what would that do?
Well, the compressor spun the wrong direction, the lathe spun the wrong direction, every three-phase motor in the building. The mill
What's the
spun the
wrong
wrong direction. So when I hit reverse, it goes forward, and when I hit forward, it goes reverse.
When you turn the bandsaw on, it went back.
Well, the bandsaw is single phase, so that's a different story.
Okay, how about the drill?
The drill is also single phase.
Give me a three-phase out there.
The lathe, the mill, the compressor,
Okay.
I forget, there were some other, a couple of the blowers.
How do you know they're three
Compressor
phase?
loaded to the side.
It just spun backwards. Now, with that type of, the type of compressor we have there, when it spun backwards, there's this weird unloader valve that caused it to do all kinds of weird stuff. That one was sort of bizarre. It made all kinds of funny noise. So rather than rewiring it, I called the compressor technician out just to make sure that it didn't break anything running backwards. But yeah, just mind-boggling. So, three-phase motors, we're not going to worry about too much because they'll do exactly what you do in terms of wiring them. And if it's backwards, you just reverse 2 leads, any 2 leads. Any of the 3 leads, reverse 2 of them, and it'll go the other direction. You'll begin to see this here in a little bit when we start talking about single.
So they just had to go out to the main panel and switch the leads.
I just did it on all the motors.
Oh, you did? Okay.
Are you kidding calling them? So I called him one day because the lathe stopped working. I figured out it shorted one of the wires, one of the 3 phases inside, 440, inside the walker duct. So the guy comes out and he's looking at it going, yeah, and I said, it probably blew L1 there. Yeah, and in fact, you can pull the wire out and it's blown apart. And you go, oh yeah, okay. That means it also at 440 volts probably fried all the other wires in the walker conduit. Said, yeah, they're all still working, so, and I wasn't contracted to look at them, I just fixed the one problem. So if you see them, you have to fix it. He's like, well, yeah, if I see it, I gotta fix it. But so the next day he came back, showed up to fix it. All the wires were neatly laid out on the floor. And he could see where they were all fried. Somebody overnight had taken all the wires out of the walker conduit and laid it on the floor so he could see them.
How long did it take you to do that?
About an hour and a half.
Okay.
But it was like, you know, I just mind-boggling. So there's working on electrical and dealing with the politics of large organizations.
Not fun.
Okay, so there's a variety of different kinds of things here. I'm going to talk a little bit about, so AC motors actually, this is a little difficult statement to make, but the big advantage of an AC motor is in the grand scheme of things, I can get a lot more power for quite a bit less weight and less efficiency, or excuse me, increased efficiency. But note that I've said power, okay, not torque. AC motors, typically even large ones, aren't very torquey. They take a little bit to get going. Not like a DC starter motor, which they can, so they do not produce as much torque as the DC equivalent, but they can produce quite a bit of power. It's pretty hard to make a 15 horsepower DC motor. It's pretty hard to do that. 15 horsepower AC motor, not a problem. Okay, pretty straightforward. That one in the generator test stand's a 10 horsepower. It's a pretty good sized unit, but it's smaller than a 10 horsepower engine, a whole lot quieter. So obviously the downside of AC motors is they don't work so well with batteries. And so really, if you need a lot of torque or you need to run it with a battery, AC isn't a good option. If in fact you can run with AC, and particularly you can start it somewhat unloaded, then it's by far and away the best option. They do make universal motors that are both AC and DC. You don't see too many of them. They're not very, it's like a starter generator. They're not very effective or efficient, so I don't talk too much about it. So let's talk about the induction motor. So if I take some magnetic fields, and I take, let's say I just take a magnet, physical magnet, and I start spinning it around a barrel, okay? And I have a piece of iron in there, okay? Or I have a bunch of iron bars all hooked to a little spindle. As I start moving that magnet around, the magnetic fields are going to start cutting those iron bars, right?
Mm-hmm.
And as they start cutting those iron bars, aren't they going to induce some current flow in the iron bars?
Mm-hmm.
As they start producing current flow in the iron bars, in this little spinny thing, that current's going to create its own magnetism. And that magnetism will start reacting to the magnetism that I've got spinning things around. So that set of magnetic bars hooked on a spindle will start trying to follow the magnet. Now it has to have some slippage, but it'll start trying to follow. Now instead, if I took all those iron bars out and just put a big magnet inside there, and then I took my magnet outside and started spinning it around, the magnet would stay locked. Okay, the spinning magnet would stay locked with the outer magnet. South to north, north to south, they'd just stay right locked with each other. In other words, they'd stay in synchronous. So the advantage of the AC winding coming in is instead of taking a physical magnet and spinning it around like this, if I take and wind my three fields correctly, it'll cause a band or fields of magnetism to form just like they did if it was a permanent magnet, and to physically move around. So in the case of the induction motor, Mr. McKinder, in the case of the induction motor, we're going to have this thing, this armature spinning around inside, constantly trying to keep up with or catch up with the magnetic fields spinning around it. Now, it has to have some slippage, or it's not going to generate its own internal magnetic field. So another way of saying this well, let's look at the picture first. So if I take my 3 windings from the generator, and I feed them in depending on which way the current is going. So now the current's going like this, then it's going like that, then it's going like this and like that, and then it's going like that, and it keeps on consecutively. What you're going to end up with is magnetic field, then magnetic field, then, actually I'm going the wrong direction. Magnetic field, then magnetic field, then magnetic field, then magnetic field. And as this one begins to decline, okay, this one will decline and jump to here. This one will decline and jump to here. And these two out here will form with those to make that. And on and on and on.
Are each one of those a different, like when it comes around, is each one of those a different phase?
So I've got a winding phase 1.
There, phase 1.
Okay, back to here.
Okay.
And a winding here, phase 2,
Oh, okay.
neutral. And then the winding here to there, back to the middle.
Oh,
Okay, they're all coming to the common point in the middle.
okay.
Okay, so in this case, it's Y wound. And most motors are Y wound. There are some that are delta. Almost always are Y wound.
What's the other one? Delta?
Delta is the triangle winding, right? The reason we do that is, the reason we Y wind them is because we can double the voltage or double the current.
Oh.
Okay, so this then sort of shows, they tried to sort of do it, this particular drawing tried to do, showing you the different circuits. So A1 to A2, north-south, C1 and B1, and then as depending on which, where it is, so this one, when this one is high, it sits here. When this one starts coming up high, it gets like this. Then when this one starts coming up, where am I? This one starts coming up high, it's off like this, and on and on and on. So as you can see, this is rotating just a little bit each way. And that would be the same if I took a big magnet, right? North pole, south pole, north, south, right? Ding, plop, 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 going a third of the way each time. Okay, or a 1/12 of the way, or a 1/6 of the way, depending on how it's wound. Okay. So another way of drawing this is if you took a row of light bulbs like this, and I turned that one on, left the rest off, or let's do 2 to represent north and south. So I turned those 2 on, left the rest off. Then I turn these 2 off and go to the next one. And then these off and go to the next one. And if I do that fast enough, it's going to look like these 2 lights are rotating around, aren't they? Well, in fact, because magnetism is slow, it's not instantaneous. If I electrify these and there's a magnetic field, I'm going to turn the magnetic field on, then I'm going to turn it off and go to here. So the magnetic field that was here is going to start collapsing, but then shift to here as this comes on. Then shift to here as this comes on. Then shift to here as this comes on. And it's going to keep shifting around and around and around. Just like if I took a big magnet and was rotating it around. Well, ultimately, by feeding, as long as I'm using some division of 3, actually some clean division of 3, 9 doesn't work. So 3, 6, 12, 18, etc. as long as I'm doing that in terms of the number of windings for each phase, then this thing, in truth, this is doing it, then another group of 3 is doing it, then another group of 3 is doing it, and they're all moving around, okay? And of course, they're going to react against the armature because the armature is either a permanent magnet or I'm going to induce some energy in it, okay? So in this example, the bulbs aren't physically moving, are they?
No.
But sure looks like they are, okay? All the LED display panels that you see, like right up here, okay, they create all kinds of motion on there simply by turning all the little pixels on and off, right? Okay. This shows another sort of example of it. So the rotor in this particular case, we often call it a squirrel cage. It's it's just a bunch of bars stuck in a can-shaped configuration, put on a spit. Let me see if I can show you an example of that. I got a little one here. This is actually only just the very end of it. It's probably about a 20 horsepower electric motor. So note a bunch of laminate plates in here. Okay, each one of these big aluminum bars are the magnetic fields are going to be cutting through at right angles to these big aluminum bars. So in these big aluminum bars, current is going to develop because the magnetic fields are cutting them. Well, as current starts to develop, you're going to get magnetic fields running this direction, which are now going to be at right angles to the magnetic fields, inducing the original current. So just like we said in the DC motor, one side's going to push, the other side's going to pull. This guy will start trying to follow it. Okay? It'll start trying to follow those magnetic fields spinning around. If it ever catches up, there'll be no relative motion between this and the magnetic fields, so the induced current in here will go away. Okay? So it has to slip some, that bottom note. It has to slip some. Well, how much does it slip? How much are you going to grab the end and slow it down? If you grab the end and slow it down, it's going to induce quite a bit more current in here, induce quite a bit more current in the original field. Of course, the current going into the motor is going to go up because you loaded it. And it'll find some new happy balance. Okay? If you unload it, it's going to probably spin up a little bit and then find some new balance and just sit there loping along. Okay, so that principle that we said that the load in a circuit will always match the input until something fries. Okay, so in other words, like a transformer. A transformer sends energy through. If I don't have the other end of the transformer connected to anything, that because of inductive impedance or inductive reactance, the primary side of the transformer becomes infinitely resistant. Okay, and the current almost comes to a stop. So a transformer at idle uses almost no current, even though it's a dead short in the AC circuit. Same thing is true here. This guy, when I first turn it on, lots of slippage, a whole bunch of current. Once it gets up to speed, its current's going to start dropping because this guy's going to catch up. And it's going to start inducing less and less current in these windings. Okay, less load on their initial inciting windings. Don't just sit there fat, dumb, and happy until you take and put your drill into the grinder and start grinding it down just to annoy your general teacher. Okay. All right. So this is called an induction motor. There's a drawing of it. Okay, we just have a couple of plates with a bunch of copper bars. Well, in truth, we want to help the magnetic fields go from pole to pole. If we just fill the inner with air, there's nothing really to help the magnetic fields cut all the way across. So if I take and put a little plate in here, now the magnetic fields have a permeable, a magnetic conductor, little steel or iron plate, right? So the magnetic fields definitely want to form across here. And they'll follow around real nicely as they're going around and around. Now I have to make a whole bunch of these plates so that the magnetic fields induce current this way, but not this way. Okay, so we're going to magnetically separate the plates by just a little bit. There's not much here, it's just a little bit of light shellac. Okay, so kind of like a little squirrel cage. Let's go to the other end of this text. Little bitty lightweight motor. You can't really see it in here, but if I took that out, you'd see a bunch of little bitty bars in there. Okay, bunch of little bitty bars. In this particular case, instead of having 3 phases, we're only going to have a single phase going to this thing. So what's going to happen is it's going to build up the magnetic field, and then flip around, build up the magnetic field, and then flip around and build up the magnetic field. So this thing isn't really going to know which way to start unless we play with it some. Okay. Oh yeah, so here's a picture of a typical squirrel cage induction rotor. No brushes. Nothing, no brushes are needed because we're going to induce the current. This field, AC field, is going to induce current in here. The current that's induced in here will create its own magnetic fields, which will try to follow that original AC field. No, that's kind of confusing, huh?
Mm-hmm.
Sort of seems like perpetual motion. But as long as there's some slippage, it works. So, if I increase load, obviously RPM is going to decrease. As RPM decreases, the rate of slipping increases, therefore the amount of cutting increases, therefore the amount of induced current in each one of these bars starts to increase. As well, the amount of current being now driven through the original windings goes up, causing this thing to try to spin with a little bit more force to catch back up to the original RPM. Now, of course, it doesn't ever catch up to it unless I turn the voltage up, right? Okay. Now, if constant RPM was real important, then I would have to do something to monitor that. In most AC motors, we don't care what the RPM is, do we? I mean, it's kind of nice to make sure the blade keeps cutting at about the same rate, but that's more a function of just don't try to shove the wood in too fast, right? Okay, as long as I'm not getting too crazy, it'll stay pretty close to the same RPM. And the blade is truly allowed to cut rather than being forced through the material.
So could this be a typical example is just the skill saw, worm drive, skill saw?
And even non-warm drive.
Okay.
Yeah, anything you plug into the wall that's a motor that spins round and round, almost all of these are induction motors. Okay. Now some of the smaller ones, they're DC motors with a AC inverter in there.
Okay.
Excuse me, a rectifier in there. Some of them will do that. The variable speed ones, they're expensive, but it's cheaper to convert to DC and then do variable than to use a varactor. Okay, so self-starting these guys is a little difficult. Let's see if I have a way of doing that. So the case of the light bulb, if I really only had 2 light bulbs, which is kind of what happens when I do single phase. Okay, well, I might have a bunch of winding. I really only have 2 light bulbs. And I'm going to go turn it on one way, and then turn it on the other way, and then turn it on one way, and then turn it on the other way. So the magnetic pull is going to be very linear, right? I'm just going to be pulling this way and then pulling that way. There's no sort of pulling. I'm pulling this way and that way. There's no pulling at a slight angle. If I could pull at a slight angle, then I could get this thing to start moving. And the truth is, if I take this and just go like that, nothing happens, right? It's not until I give it a start and then start. See, now I'm just going straight up and down. But I had to do something to get it started, right? Once I got it started and some inertia going, now my finger is just going straight up and down. Whee! Until it goes flying off in about a high-speed RPM, right?
There DC assist. Is there like a DC assist motor to start much larger AC stuff?
Yeah, you could do that. There's easier ways to do it, though. There's easier ways to do that. Remember we talked about inductive reactance and capacitive reactance and how capacitive reactance can distort inductive reactance? Well, if we take and run this winding through a capacitor, instead of having the straight pull, we're going to start creating a little bit of a distortion in the pull. So the magnetic field that's trying to pull straight across is now going to form just a little bit of an S curve to it. Okay? I can do that with a big capacitor. The problem is, once I get this thing going, I don't want to keep the capacitor running because it's going to get hot. We're going to really load the thing up. So we're going to use a capacitive reactance to phase shift the original inductive reactance to try and get this the magnetic fields to shift off just a little bit into a little bit of an S curve. Then once it comes up to speed, we're going to kick the centrifugal. We're going to use a centrifugal switch or some other device to kick the capacitor offline. Some other way of kicking it offline. So you know, all the AC motors you see, bigger motors, have a big bump on the side. That big bump is the capacitor. Okay, that big capacitor is a starting capacitor, and we use it just to distort things a little bit. Now this is one way to do it, and it's a fairly powerful way of doing it. It also helps produce a little bit of extra torque. So that actually helps a fairly large motor get started. Smaller motors, there's another way of doing this. AC motors, there's a slightly different way of doing that. It's a lot easier to make, and it's a lot more reliable. Okay, so again, don't need it with 3-phase, but with single phase, the capacitor will take and start splitting the current phase from its normal behavior, causing a little bit of distortion in the magnetic fields. And then once it comes up to speed, one way or another, we'll take the capacitor offline. So that's what this shows. So this shows your primary windings, okay? Then you're going to have a secondary winding coming through the capacitor, and that's going to split this field out of phase slightly with the primary winding. These two windings here are going to distort the magnetic fields enough to where instead of pulling straight across, they'll do an S like this. They'll distort some. And so as they pull, instead of pulling, they're going to kind of go this way a little bit. And that's going to help it go a specific direction. Right? And then once this comes up to speed, something kicks that offline. All right. Now another way of doing this is we're already going to be inducing magnetic fields in the squirrel cage, right? Why don't I take my field pole and put another little wrap around it, sort of off asymmetrical wrap around either side, that will also induce some magnetic fields, or a little bit of current, and that'll actually distort my magnetic field a little bit. Just cause it to a little bit. If I don't have a lot of load, I can shade my original field a little bit with some counter-magnetic fields, and once things are up and running, I'll just leave them there. I don't care. This ends up being really, really simple. So what I'm going to do, without my shading, and this stupid little thing keeps getting on. So without any shading, the magnetic fields are going to build up and collapse and build up and collapse. But by taking and wrapping a little bit of it with just a conductor, copper conductor will work. A little bitty copper conductor will work. That's going to cause these guys to form just a little bit of an S-curve. And that S-curve, instead of pulling straight across, is now going to pull at a slight vector. That's going to be enough to get this thing to go the direction I want it to go. Now, if I wanted it to go the other direction, what I would do is I would put this over here and that over there, and it would go the other direction. Okay, note the similarity. Only it's kind of like this here. Yeah. Okay. So as the magnetic field builds up and collapses and builds up and collapses, these guys get a little bit of current going around this way, which then distorts the magnetic field enough to where it's now going to be shaded this way and that way, which is going to pull this direction. You guys don't believe me, do you? Well, let's see if the drawing is correct. So the shading appears to be the same way. So this should spin this direction. Now this is a centrifugal fan, so we don't really care which way it goes. But we do want enough to get it to start. So, but according to that drawing, this should spin that direction. Now either the drawing's wrong or it's right. Oh, not plugged in. Okay, let's plug it in here. Okay, it's spinning this direction. Ouch. One of the things about these things is they have absolutely no torque. I mean, just poof, you can stop them cold. No, they're not quite cold. Okay, no torque. There's not much mass here. That one, it's got some mass. Once it got up and running, it's got some inertia, right? This one, I'm going to have to use a capacitor to get it going. This guy, is there any load there? No, all I need to do is just to get it once. And of course, once it starts, it's just like the little cord on my finger. Once it starts going really fast.
Did you?
Extension cord.
I don't mean to ask, but how do you charge the capacitor if the AC motor?
I'm not charging it. On the back one, give me back one. So on this one, it's just straight in line. AC passes right through it.
Oh,
Right?
which gives it. I guess.
And that causes that winding to be out of phase with the original magnetic field. So this guy, and it's a much smaller winding. All it's doing is distorting the field some, just like the shading did in this second example. Okay? All we're trying to do is, in this case, the previous one, we just had another winding creating that distortion. Okay? It'll produce quite a bit more distortion and quite a bit more torque. So it's better for a high heavy inertia type motor here versus a little bitty bathroom fan motor. Okay, how many moving parts are there? Okay, I mean there's one little thing in there spinning around. That's it, a couple of funky little bearings. And as long as this thing doesn't have to start with a lot of torque, it'll go like a banshee. How fast will it go?
I don't know.
Well, one of the things that's going to be
Number of windings?
a determinant factor is going to be the original frequency of the AC going into it, right?
60 hertz.
Okay, 60 hertz. If I put it up to 6,000 hertz, it'd probably go a lot faster. And that's, in fact, the hertz are what really make it very difficult with an AC motor to vary the speed of the motor. If you want to vary the speed of the motor, the most effective way is to use a varactor device, which changes a varactor. I'm not saying it right, which changes the frequency. It's a pretty complex set of circuits and not too cheap. How about all the different little squirrel cages in here? All these little, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, that's the wrong number there. But if I added more, it would go slower. If I added fewer, it would go faster, but probably not have as much torque. Okay. I can also make them really wide or very, very narrow and small, which would change its rotating speed some. Okay, and this is sort of showing just sort of the way the pole's happening. So if I go north, south, north, south, north, south, that guy tends to follow it round and round and round. Now again, if instead of using this, I take and put a big magnet in here, and I got a big magnet bar that's a north bar, a south bar, a north bar, a south bar, and an even number of bars going all the way around, then this guy will follow the AC current. And if it's unloaded, it'll follow it exactly. Now, as soon as I start grabbing it, it's going to start slipping some, but that will induce current in it, and it'll try to catch up. Now, I can do that with a permanent magnet, or I could put a small little set of brushes and make an electromagnet and have a little DC electromagnet in the armature. And then that would follow my 60 cycle, it would lock right into it. And in fact, if it starts to slip a little bit, I could use a little voltage regulator to sense that slipping and increase the field current to make up for it. I could actually keep this thing, I could cause this guy to stay synchronous through a variety of different loading, if that was really important. Let's say it's the little machine that, I don't know, runs the iron lung, and you don't want it to slow down on you. Hurry up, I gotta breathe in, okay. So, and the way they do that is they just take a three-phase, much like our brushless generator. We just take a small DC generator or AC generator, feed it to a DC power supply or rectifier, and then feed the field. Almost the exact same thing. And that will be a very stable synchronous motor. We don't use them too much. All right, there is an FA test question. Do I care whether or not you can calculate what the speed of the motor will be based upon the number of poles and the frequency and the blah, 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 blah? No, I don't. I actually really don't care. We'll never use it to fix anything. But there is some FA test questions around it. So the number of poles that I put out there, if I only use 2 poles, I'm not going to get too much, right? But remember, if I divide it by a small number, the number of poles is going to go really fast. If I divide it by a very large number, it's going to go really, really slow. So 60 cycles per second is the AC, and there's 60 seconds per minute. So I need to know, because we're doing RPM, right? So I'm going to take 60 times 60, 3600, times 2, because you got both the positive and the negative cycle. And then you divide that by the number of poles. So note that if I only had 4 poles, I'd go 3,600 RPM. But if I had 4 poles, I'd go 1,800. If I had 6 poles, I'd go 1,200. So I could go slower and slower. But what's the difference? What does 6 poles give me that the 2 poles doesn't? Or 4 poles doesn't? I get 6, 4. Yeah, the 2 poles doesn't. This guy's going to produce a lot more rotary force, a lot more torque than the 2 pole. Okay, so the number of magnetic fields that I put around here, and by the way, all 3-phase motors, they're going to be really units of 3, and it'll be a doubling. It'll either be 3 poles, which is rare, 6 poles is really common, or 12 poles, very expensive, but very torquey. Very strong motor. Good starting speed in the world of 3-phase. Okay, single phase, you'll see 2 and 4 pole. 2 pole, you really sort of got to get some work to do to start it. 2 poles, right? Okay, magnetic, 1 pole here, 1 pole there. Not much to it. Okay, 4 pole, I put another okay, and then on. Okay.
All right, 2 pole.
So you can melt these guys down. The more I load it, the more current is going to be induced into it, because it's going to try and keep up. Remember, in the DC motor, as it comes up to speed, it creates a counter-motive force. And that counter-motive force creates an inherent impedance to the current flow, so its resistance goes up and up and up. Well, the same thing is true here. As it goes faster and faster, it's going to go up and up and up. The impedance or resistance is going to go up and up and up. And then you're going to grab it and load it. It's going to slow down. Counter-motive force is going to start declining. Induction occurring in the induction rotor is going to start declining. Current's going to go up to make up for it. So this thing could eventually get to the point that you probably won't get this hot enough to melt it, but the inciting AC windings that are copper wire wrapped with insulation or coated with insulation, that insulation will eventually get really, really hot. Okay? Now, what happens if I overload it? Well, let's see what happens if I overload it.
Let's do it.
I wish I had a plug that was high enough.
Let's do it.
Oh well. Let's see what happens when I overload it. Okay, it's spinning. It just sits there and hums. It's just like stalling a transformer. Okay, I've now got the primary winding working on the inner induction coils. They're acting like a completely open circuit in the stalled secondary, because the secondary isn't attached to anything. This will eventually get warm.
It produce heat, I was going to say.
It's slight, but it's not right now. It's not getting warm. I can feel it vibrating a little bit at 60 cycles per second. Okay, so this will behave very much like a transformer does. That's stalled. I feel it now. It's maybe 2 degrees or 3 degrees warmer. Maybe it's probably got warmer from my thumb. Then, you had a question, Mr. Juice?
No, I was trying to feel the fan here.
It's a centrifugal fan. It would have been coming outwards.
Mm.
Is there any other type? Centrifugal is the only one, right?
No.
Just kidding.
No, how about the little blower fans, you know? Those
Oh,
aren't centrifugal.
all right.
Okay. All right. So in the AC motor, we can change the frequency electronically. And again, there are several ways of doing this. If we counted on load, let's say load was fairly constant. Maybe it's driving a pump or something. I can lower the volume of fluid being produced by lowering the voltage where the pump slowed down some and I started stalling it a little bit. Just like I could grab my thumb and put it on there. Now, if I lowered the voltage, it would slow down or speed up under a constant load. We rarely have a constant load though, so it's not a very good strategy. More often, and this is why with a DC motor, if I put a big resistor in there and just turn the resistor up or down, I'm going to change the speed, right? Here, putting a resistor on there and an unloaded motor in particular wouldn't change the speed at all. It would still be, it would strictly be a function of number of poles, time, number of poles, and the frequency. Okay. So this sort of middle note there is saying the AC motors typically have two sets of windings. So there's a picture is a much better way of describing this, and I think the next slide shows that. I can wind them in delta, stacked, or I can wind them in Y, and that will change the amount of current versus voltage. The power will be the same, but by having, if it's a three-phase motor, I'll have 6 windings in there. So I can run the windings in series with each other, or I can run them in parallel with each other. If I put them in series, the voltage drop across them is going to be quite a bit higher. It's going to be less current, more voltage to run it. If I run them in parallel, it's going to be much more current, much less voltage to run it. Okay, this, and almost all AC motors are done this way. Just, it's a matter of convenience. Wind them all that way, and then if you need to take this, let's say I need to take the lathe, and I need to move the lathe down to Rico Road where we were for about 2 years or a year and a half, whatever, while they were rebuilding this building. They got 440 here. They did not have 440 down there. They only had 220 in that building they moved us to. So all I had to do was reconfigure about 6 or actually 9 wires, reconfigure the way they were attached to each other, and I converted that unit from a 440 to a 220. Now it was using quite a bit more current, doubled the current, but I was still able to use it down there. Brought it back up here, I rewired it back to the way it was, works like a champ. Now the regulating switch, I also had to put a higher current regulator in there, but okay, so I think I show a picture in the next. Yeah. So whether it's a Y-wound or a delta configuration, so in this particular case, what I can do is I can wire these so that I have a series Y, or I can take these guys and bring them in and have 2 parallel Ys. Same thing is true here with the delta. I can do the similar arrangement. I can either have in series delta or 2 delta in parallel. And all I'm going to do, the windings are in there, and I'm just going to have these little wires come out. All I have to do is take and wire them this way for high voltage, that way for low voltage. Okay? So in this particular case, I'm bringing all 3 together at a common point there. Whereas in this particular case, I'm keeping them all individual with a common point coming out there. Same thing is true in the delta configuration. So I can actually wind this motor any one of 4 different ways. Now what's the most efficient? That one right there. The high voltage Y winding is the most efficient, 3-phase, by just a little bit.
This is a good test question.
I don't know actually that the FAA goes there, but essentially like this, sometimes called star, but Y wiring, high voltage, because we put all the windings in series with each other rather than 2 Ys in parallel with each other. Okay? And 3-phase is always way more efficient than single phase. All right. All right, so AC, it's kind of confusing, huh?
Mhm.
Yeah, sorry. They work really well and they're bullet simple to make. I mean, basically, I'm going to take a housing with a bunch of wires wrapped up in it, and the wires come out. I'm going to take this guy, which is just a big metal shaft, put a bunch of these little plates on it, an aluminum fan end cap, right? And then shove some bars down in it to clump them together, okay, and sort of fuse them into the end caps. A couple of bearings, it's done. It'll spin, it'll work. But conceptually, they're a little confusing. But in the real world, they're they're pretty easy to make. Okay, servo motors. Now, let's talk about the need for precision as we make our motion. In the case of this guy, do we care where the armature is at? No, as long as it's spinning, we're happy. Okay? All that burrito smell is being sucked right out of the bathroom. Yeah. Okay, but we don't care where it's at. This guy, though, it's driving the flaps out. We kind of care what position, we kind of do care what position it's in, right? And we actually want it to go to some point and stop. Okay, we don't want to keep putting the flaps down to the point the plane crashes. Okay, or suck the flaps up to the point that something breaks. Okay, so precision begins to matter. Where precision begins to matter, we start using the term servo motor. Now, there are some vernacular elements here. We have basically 2 categories of servo motors. And some engineers refer to one as a stepper motor and one as a servo motor. They both operate by a similar function of being able to take the armature and move it a finite amount. And then move it again a finite amount. And then move it again a finite amount. And move it again a finite amount. And they may string these together, finite, so that it's actually spinning at 7,200 RPM or 5,400 RPM, but it's still going clunk, clunk, clunk. It's just not stopping in between, right? In a true stepper motor, it's just going whatever direction it's going in a finite amount, but it doesn't really know where it's at. A true servo motor has some type of an encoder or something in there that also tells it where it's at. Okay, this guy, the motor doesn't know, but the little limit switches tell when it's at either end. Thunk, thunk. Anywhere in between, it doesn't know where it's at. A common strategy for many of these servo type devices is instead of using an encoder, when you first turn it on, it has no idea where it's at. But it knows to count how many times it's moved, how many positions it's moved. Okay, maybe it's 36 elements per revolution. It can count that if it can get a starting point. So like your laser printer or your inkjet printer, what's the first thing that happens when you turn it on?
Reference it.
So it's going, that's moving and doing all this weird stuff, right? Well, what it's really doing is it's finding home. It's going till it hits a limit switch on several of the different components in there that move. So once it finds home, every time after that, it's just counting elements of a revolution. And it always knows where it's at once it's found home. Now, what happens is, a lot of times they can lose that. So most of the time, the program behind these guys that don't have encoders is, before they do anything, they go find home. Just like before you solder, clean the tip, right? Same thing. Before it does anything, it goes find home and then does its job and then shuts down. Just because home can get lost. The higher end motors have an encoder that tell it where it's at with respect to not only rotation, but if it's driving a shaft, the shaft will have an encoder as well. So if you turn it on, turn it off, and turn it back on, it goes bada bada bing, I'm alive, my encoder tells me I'm right here, everything's good. So maybe the drive motors for a mill, okay, maybe they need, the precision mill might need to have an encoder, okay. You still have to reference 0, but versus the laser cutter right there, its big step or servo motors does not have an encoder. First thing you do is turn it on, get everything running, and then tell it to go home. And it goes boom, and finds home. The next thing you do is you then set depth to meet the right focal length. And every time you turn it on or reset it, you've got to do that. The upside of these guys is they are extremely precise. With gearing, driving, belt drive, pulleys, etc., I can get these things to very, very accurately, well, you see it, right? Yeah, I don't know where they went, but you guys saw them going around. They can very accurately position an engraver, a mill cutter, a laser, an ink cartridge, okay? All right. So a stepper typically doesn't know where it's at. And again, I never found any solid consensus on this. But a stepper motor, so for example, your hard drives, those of you that still have hard drives, the thing that's driving the data platters, that's a stepper motor. And it's going to go thunk, 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 it just won't stop. But it knows exactly where it's at. Once it gets started, it knows where it's at, reference to an initial starting point that's actually cut on one of the platters. A little magnetic starting point. Okay, servo, as soon as it turns on, it knows where it's at. Now, the other thing that's interesting about most good servo motors is a stepper motor, once you unpower them, they can free spin. Okay, just like that fan, they can free spin. They might not because of gearing, but they can free spin. Whereas in a servo motor, I can actually use electricity to spin it and use electricity to stop it and lock it.
How do you spell Stepford?
Stepper.
Stepper.
Stepper. Not Stepford. Stepford is like that really weird movie.
Yeah.
Oh yeah.
You have a desktop at home?
Huh?
You have a desktop at home? You have a desktop?
A desktop.
Yeah. Do you have a desktop computer at home?
No. I don't use desktop computers. Laptops only. I stopped using desktops probably about 15 years ago. They break all the time. I also stopped using Windows, which is part of the problem. But we won't go there. So servo motors, really precise, very, very accurate. They've gotten so effective that we're now starting to use them to control airplanes. Okay, Airbus has actually been using them for some time. Boeing 787, which by the way, I was in formation with one the other day. It's kind of fun. The 787, all the flight controls, spoilers, everything else, all being run by big, powerful stepper motors. High degree of speed and really high degree of accuracy.
No hydraulics. No hydraulics.
No, I don't. So, this is an example of a stepper motor there. And as I light off the fields, note that they're staggered slightly a little bit. So when this guy's lined up, that guy isn't, that guy isn't. So I light up that field, and then I light up that field, then I light up that field, and this guy's gonna move a quantified amount each time. Now, also note that this is spinning at some speed,
Fast.
okay, like a driver. I'm gonna get it spinning fast, but I'm gonna know exactly where it's at. And if I, in fact, needed to be here and I passed by, that's okay, it's spinning so fast, I'll just wait till it comes back around again to that same spot, and then I'll get what I want from there. Okay, so one example of the stepper motor. And in this particular case, I've got 4 individual fields that I'm going to control with the computerized circuit, turning each one on and off in some sort of synchronous manner. And so in this particular case, we'd have to count it up, but it looks like it's going, that's a little hard to say, but I'd have to count it all up. But it looks like, to me, in each cycle, it's going 1/36 of a turn. So it would take 36 full cycles for it to get all the way around. Now, of course, there are a variety of different ways of doing it. This one, instead of having just 4 windings, note how it's got quite a bit more. Okay. This is an example of the actual outside stepper motor. This one's slightly different. This is just a drive servo, but it's not nearly as precise. So it's going to drive one way or the other way or stop. And if it's not moving, this screw gear does a pretty good job of locking it in place. Okay. Now, this particular device up here is the encoder I was telling you about. This is something that as the drive motor spins, it's going around and it has a little light and a receiving element that then tells it how far it's moving. And oftentimes what they'll do is they'll make one of these windows slightly odd shaped. That tells it that it's gone a full revolution. Okay, so that little encoder does a pretty good job of telling the motor where it's at. In terms of per revolution, it does not tell it where the motor is at in terms of which revolution it's in. So that's only a partial encoder. Well, I say some servo motors. What's really happened is we've developed hundreds and thousands of machines that run off of servo motors. So because of that, we've designed code as well as unit control, small dedicated control circuit that we commonly call drivers to drive the servo. So what I'm going to do is I'm going to say, I'm going to use some instructions code and send it to the driver. The driver is physically going to turn off and on a variety of different transistors to get the motor to do what I just told it to do. So I'm going to have this little miniature computer that's dedicated to causing the servo to run. And that little bitty computer is expecting to see some binary set of instructions. Okay? And there are a variety of different code sets. What we typically use in the world of like 3D printers, the laser, CNC mills, we've been using a code that's been around since the early 70s, I think, called G code. There's actually about 213 or something like that different commands, but the bulk of all the commands that are used are less than 10. I mean, literally, it's straight line from here to there, X to Y. Okay, draw a curve based on a radius. That's another instruction. Okay, if you have a sort of weird curve, what you do is you just put a whole bunch of little bitty straight lines, all put together into making a weird code. You just send it a zillion set of instructions. It's going to cause it to go a little slower, but that little sample piece that was going around, the little curly QY, that's just you know, I don't know, 5,000, 10,000 lines of code that cause it to go versus a constant rate of current of turning. Okay. So again, I'm not ever going to test you. I hope the FAA never tests you, but there's a variety of different ways of feeding it binary data and overlapping the different windings to get it to move just a finite amount. Very precise. The other thing I can do to increase precision is increase the gearing. Okay, if I put several gear assemblies in there, now each full revolution only represents 1,000th of an inch travel on the mill bed. Okay, man, I can get that. If I get 10 full stepper motor revolutions for 1,000th of an inch travel, I got some pretty good precision there, right? Okay. So, and then this is sort of what I talked about, like your drive motor. So the stepper, this is a little stepper motor that sits inside the head, and that's moving a finite amount. And in fact, what happened is we got into the nature. One of the things that takes a lot of time for the drive, your hard drive, is it's spinning around. It takes a lot of time for the head to move back and forth. So what they did is they stacked a bunch of platters together, and they had, you know, 5, 6, 8, 10 read heads, and they would read all the data on all 5 heads at the same time. So rather than looking at this like a bunch of platters, they looked at it like a bunch of cylinders. Okay? And so each 5 or 10 or whatever number of heads would read a section of data along this platter, the next platter, the next platter. And it really was reading multiple data reads at the same time, all then being packaged together in the computer here and sent out as a file. Okay? Down here in the middle of all of this is, in the center where it spins really fast, is all the instruction sets for where each file is located, or the file allocation table. You guys might have heard FAT, right? FAT 32, FAT 64. So what's going to happen is you tell the drive, I want a file. The head's going to go inside, it says, I'm going to find out where the file is. In there, it'll go to the file allocation table, and it will tell it where each of the little bits of data are stored. It'll go back out, get all those bits of data, rearrange them, put them all back together, and then send it to you. Okay, these servos have been around a long, long time. These guys are so sensitive. This head, as it's flying across the surface of the platter, the platter is actually moving, and it's stationary, but from the perspective of the head, it's flying in ground effect, about several molecules above the surface. And in fact, most of these drives, if you take them up to high altitude, they'll depressurize a little bit, and you start getting head crashes. Now they've gotten better at pressurizing them, such that they'll work just fine in like in most airplanes. But the old
Why can't they use solid state?
now they've gone to solid state in the last 4 or 5 years. However, solid state doesn't hold as much data. Okay, a 5 or 10 terabyte solid state drive, that's going to cost you a little bit, and they don't work as fast. Okay. So the inherent position servo is that guy that doesn't really know where it's at. Every time you turn it on or every time you use it, you're going to have to go find a reference point. So your printer is a good example of that. 3D printers, the low-end drive, mill drives. Now, the kind of servo that actually knows where it's at, what's a really common example of one that's been around for many, 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 many years? It's a form of servo, and it knows where it's at every time it turns on, because it has a little encoder in it, really in the form of a switch.
Clock?
No, clock just goes round and round and round. You know, it's been around way longer than that.
Printer.
No, way longer than that. Man, it goes all the way back to the 40s, 30s maybe even.
Wow. That's old school.
Old school.
Yeah.
It's a servo, and it
What?
knows where it's at when it comes on.
What did you say? What was the answer?
Huh? I haven't said the answer.
Oh.
He hasn't said it.
You reach forward in front of the steering wheel and go, what moves? Windshield wipers. Yeah. And they got to know where they're going, right? Because you don't want them to stop right there. Okay? They know they're here. They're going to go. When you go like that, and what's up here, it still comes all the way till it hits the encoder. It's usually just a switch and says stop. Okay? That's a really early example of this kind of, kind of a setup. It, in fact, is a servo that is internally encoded. It only has one position encoder, but that's okay. As long as it always comes to home and sits there, then it'll always be starting from there. And yeah, you can get them installed incorrectly. So, boy, the sky's the limit. Got all kinds of different linear actuators, servos. Here's one that's controlling air, one of the air passages. Actually might be a compressor stall valve that's now being controlled with an electric servo rather than a vacuum modulator. This is a 787 diagram. It's showing the Ethernet-based bus. There's actually redundant buses. A variety of different servos all throughout. Okay, triple redundant actuator controllers, triple redundant actuator controllers, and on, double redundant actuator controllers, etc. Sensors and actuators, all electronic. So you guys are going to have to get to know how to play with these guys. What I will tell you, though, that's kind of useful is they do tend to be self-diagnosing. If I start getting a winding short, the computer can measure that. Okay? The computer can also measure if it has an encoder. It can say, I just sent this message to turn this servo X distance, and it didn't go that distance. Something's wrong. Warning, warning, Will Robinson, something's wrong. Okay? They can self-check, self-diagnose really effectively. So that's kind of useful. They're pretty simple, and if we make them with a little bit of precision, we can actually make pretty quality units that are far superior in terms of reliability to anything else like hydraulics or pneumatics, etc. Yeah, I don't need any hoses or any plumbing. All I need is a little wire. A lot of little wires, but a little wire. And actually, truthfully, if I'm using a networked system, I don't even need that many wires. I just make network A, network B, and network C, and they're all listening to all three. I might have some digital strategies like a heartbeat and a few other, sort of signifying data sets that tell all the different components that everybody's good, everybody's doing the right thing. Okay. But that's all a function of just design. Right? Once I set it all up, I got something that's way less maintenance. Well, maybe we don't like that. Maybe we actually want something with a lot more maintenance. This might not be such a good thing after all. Puts us out of work. Well, I don't know. As long as Southwest keeps throwing blades through the window, we'll have plenty of work to do, right? Well, it turns out for many, many years in the world of airliners, we relied on customer air. We made the turbine engine produce more air than it needed for thrust. And then we relied on that air for pressurization, heating, cooling, a bunch of other things. That then caused us to be quite a bit more inefficient. It also caused us to make a whole lot more noise, which made us even more inefficient because noise is wasted energy, right? Well, what we figured out is if we just use big generators, get rid of all that extra air we're producing that we don't need, we can turn the generator off if we don't need it, or turn it way, way back down. Okay? Then our engines can be a whole lot more efficient and a whole lot quieter. I have to tell you, I got to see the first public flight demonstration of the 787. That airplane is actually now in the Pima Air Museum. But they came by at about 500 feet overhead. I was up there in the Seattle area, and it was so quiet. You actually couldn't hear. Usually you could hear a fair amount of turbine inlet noise, the engine inlet noise. You couldn't hear it until it was almost like right there. I said, oh, wow, okay, I'm hearing, I'm watching, I'm not hearing, watching. And then, of course, as it went over, way quieter. And it was a cruise level flight, low altitude, so the power wasn't up. So yeah, these guys are pretty useful. You're going to find yourself, you're going to work in airplanes, you're going to be finding yourself using these. The other upside of most of these guys is most of the stuff is modularized. You pull it off, put a new unit on. A lot of all the drivers, the servo motors themselves, they're all mass produced. The ones that go into aviation, the aviation sort of bucket, they get a much higher level of quality control as they're inspected coming off the assembly line. But they're not doing too much in the way of special development of this stuff. So for you guys, it's electrical, right? What can go wrong? An open, a short, a failed power source, or any one of the above. Right? There's not much else. If the programming's bad, the programming's bad. You're not going to fix that. Engineers got to fix it. Right? So bad installation of wiring, connectors, corrosion, etc. Those are the kinds of things that are our realm. All right. Time for break. How about we